The string matching problem aims to find all the occurrences of P in T, given that T is a string of characters of length n and P a pattern string of length m. String matching algorithms have been developed to find the most efficient way to solve this problem. You will come across these algorithms in many areas of computing, from searching on Google to parsing grammars. There are many different algorithms with varying degrees of ease and efficiency that can be used, but today we will focus on the Knuth-Morris-Pratt or KMP algorithm.
I'm going to explain how the Knuth-Morris-Pratt algorithm works and then go through an example. The algorithm consists of two parts, the pre-computation or prefix table construction and the actual matching. The aim is to find a pattern string within a target string. KMP is different to the naive method in that when there is a mismatched element and we found j-1 elements that do match, we don't restart the matching from the start of the pattern string. Instead, we take advantage of the j-1 matched elements to tell us where to restart the matching from. Let's take an example. Let's say that we have ZA, ZAB as our pattern string, and this string matches the first four elements of our target string, but mismatches on the fifth element, aka our target string looks like this, ZA, ZA question mark, where the question mark denotes the mismatched fifth character. Instead of going back to the start of the pattern, we can just go back to the third element in our pattern, a Z, and compare this against the question mark in the target string. As you can see, the first two elements, Z and A, match up with the Z and A of the target string above. As you may or may not be able to tell at this point, we never go back and compare anything in the target string again, unlike the naive method. This is all made possible with the help of the prefix table. The prefix table tells us where to restart the matching process when we have a mismatch. In more basic terms, it tells us if there is a suffix in the pattern that is equal to a prefix. Let's go through an example. Here, P denotes our pattern and pi denotes our prefix array. We look through each element in the pattern in turn, looking to see if there is an element at the start of the pattern that corresponds to the element that we are looking at. We always start with the first element, and this always has a prefix value of 0. This is because there is nothing before this element that corresponds to this element, because it is the first element. We then look at the next element. We look to see if there is anything at the start of the pattern that corresponds to this element. In this case, A does not correspond to anything at the start, aka A does not equal Z, hence this gets the prefix value of 0 also. Moving on to the third element, a Z, we see that this does in fact correspond to the Z at the start of the pattern, so we put 1 into the prefix value. This 1 tells us that the Z corresponds to the first element in our pattern. Moving on to the fourth element, since the previous element has a prefix value of 1, we compare this element to the second element in our pattern, aka the first A in this case. Clearly these match, so we put a 2 into the prefix value for this element. On the fifth element, seeing as the previous element has a prefix value of 2, we start by comparing this B to the third element in our pattern. Clearly they do not match, so we compare this element with the first element. Once again they do not match, so this element gets a prefix value of 0. This process carries on until the end of the pattern string and we have a full prefix table. There is some pseudocode for finding the prefix array for a given pattern string, and I will go through that with you now. Hopefully you will be able to see how this corresponds with the example I just gave. Firstly, we put the size of P into M, 8 in this case. We then put 0 into pi 1, aka the first element of the prefix array, which as I said earlier always has the value of 0. We put I equal to 0, then enter the for loop from j equals 2 to 8, the size of the pattern. I is not greater than 0, so we do not enter the while loop. Pi plus 1 does not equal pj, so we do not enter this if statement either, and we put I, which is 0, into pi 2, the second element of our prefix array. We then return to the top of the for loop. I is still not greater than 0, so once again we do not enter the while loop. Pi plus 1 does equal pj, so we enter this if statement where we increment I, which is 1, is then put into the third element of the prefix array. Back to the top of the for loop. I is now greater than 0, but pi plus 1 does equal pj, so once again we skip the while loop. As I said, pi plus 1 does equal pj, so we enter the if statement. Increment I and put this into the fourth index of our prefix array. Back round again, this time I is greater than 0, and pi plus 1 does not equal pj, so we enter the while loop for the first time. We put I equal to pi I, which is 0. The while loop breaks because I is no longer greater than 0. We do not enter the if statement because pi plus 1 does not equal pj, and we put I, which is 0, into the fifth index in the prefix array. This process continues until j is equal to the size of the pattern, and we have a full prefix table. Now we have a full prefix table, and we're ready to get started with the actual string matching. I'll go through some pseudocode for the actual matching algorithm, and hopefully this will bring everything together and make it clear how the prefix table is actually used. The pseudocode for the matching is actually very similar to the prefix table pseudocode. Here, T is the target string, P is the pattern string, and pi is the prefix array. The table to the right is just to help us remember the indexes in the pattern string. Firstly, we put n equal to the size of the target string, 15 in this case, put m equal to the size of the pattern string, which is 8, and load in the prefix array. We put I equal to 0. This will keep track of how many matched elements we have so far. We then enter the for loop from 1 to m, which is the end of the target string. I is not greater than 0, so we do not enter the while loop. pi plus 1 does equal tj, z does equal z, so we enter the if statement where I is incremented. I does not equal m, so we go back to the top of the for loop. I is now greater than 0, but pi plus 1 does equal tj, so we do not enter the while loop but do enter the if statement. I is incremented. I does not equal m, so we loop back to the top of the for loop. I is greater than 0, but once again pi plus 1 does equal tj, so we don't enter the while loop and do enter the if statement where I is incremented. Back to the top of the for loop, once again pi plus 1 does equal tj, so we do not enter the while loop but do enter the if statement. I is incremented. I does not equal m, and we go back to the top of the for loop. I is greater than 0 and pi plus 1 does not equal tj, so at last we do enter the while loop. We put I equal to pi I, so we put I equal to pi 4, which is 2. I is still greater than 0, but pi plus 1 does equal tj, so we break out of the while loop. We enter the if statement and increment I. I does not equal m, so we go back to the top of the for loop. Notice that we had a mismatch, looked to the prefix value and went back accordingly, and not to the start of the pattern. This is the great thing about the KMP algorithm, and it significantly improves the time complexity over the naive method. Back to the example. I is greater than 0, but pi plus 1 equals tj, so we do not enter the while loop. We enter the if statement and increment I. Back round to the top of the for loop. I is greater than 0, and pi plus 1 does not equal tj, so we enter the while loop. We put I equal to pi 4, which is 2. I is still greater than 0, and pi plus 1 still does not equal tj, so we go through the while loop again. We put I equal to pi 2, which is 0. Now I is not greater than 0, so we break out of the while loop. Pi plus 1 does not equal tj, so we do not enter the if statement. I does not equal m, so we go back round to the top of the for loop. I is not greater than 0, so we do not enter the while loop. Pi plus 1 does equal tj, so I is incremented. I does not equal m, and we go back to the top of the for loop. From here on in, we have matches until the end of the example.
Now I will talk about the time complexity of the KMP algorithm. We'll start with the prefix table, where for each position in the target string, we are computing the longest prefix that is also a proper suffix. This can be done in OM time. The time complexity for searching for the pattern P is ON, because there can be at most n-1 successful comparisons and at most n-1 failed comparisons, which means at most a total of 2n minus 2 comparisons, giving a time complexity of order n. Putting these two together, we have a time complexity of O, m plus n. But since we know that m is less than n, we can simplify this to On, which is a linear time complexity. For comparison, the naive method doesn't take advantage of partial matches, and so, after each mismatch, only shifts the target string by one character in relation to the pattern string. This means it has a time complexity of OMN. However, because it requires no pre-computation, it won't require the extra memory that the KMP algorithm may need for its prefix table.